Hello everyone, my name is Laura Orr, and this is my talk on the paper Bootleg, Chasing the Tail of Self-Supervised Named Entity Disambiguation. This work was done with some fantastic collaborators at the Hazy Research Lab at Stanford and at Apple. Named entity disambiguation is the process of mapping from strings to things in a knowledge base. For example, if you asked your personal assistant how tall is Lincoln, the assistant would need to know that the mention Lincoln refers to Abraham Lincoln, not the city in Nebraska or the car company, to answer the question correctly. Now, this process of determining the entities that participate in text is a key part of downstream applications like personal assistance, search, and information extraction that are used by millions of users every day. For a little project history, pre-2018 at Apple, their NED system was part deep learning and part heuristic rules and hand-tuned features. This resulted in a system that was expensive to maintain and hard to scale to other locales and languages. So, in 2018, a subset of authors of this paper built and deployed a first-of-its-kind self-supervised NED system at Apple. This not only resulted in a large quality lift compared to its hand-tuned predecessor, but it was vastly easy to maintain and extend to other languages and locales. Now, the real benefit came from using the learned entity embeddings from this NED system into hundreds of downstream products across multiple languages, like Apple Search or Personal Assistance. However, we were left with a nagging question of what really was the underlying cause of this lift. And this was a hard question to answer in the proprietary environment at Apple. So we decided to start from scratch and build Bootleg, an NED system that could achieve high quality on industrial workloads. Now, Bootleg is the simplest model we could build and is open source, so other researchers can really build upon our ideas. The two key challenges learned from our industrial experiences are first, that NED systems need to have high quality in a hands-free environment without engineers. Specifically, the majority of user queries are over rare entities, what we call tail entities. Given the large number of patterns that are required to disambiguate the tail, it's difficult to scale and maintain a system that can actually memorize all of these patterns. So we're going to show how you can build a self-supervised system, which again does not require any hand-curated features, that actually uses structured data to aid tail disambiguation. And this results in a large tail performance lift by over 40 F1 points. Now, the second challenge is that these systems need to have quality with respect to the downstream applications their embeddings are incorporated into. Now, errors will occur in these downstream systems, it's inevitable. And currently, these errors are patched in each downstream system independently, which results in inconsistencies between products. So I'm not going to go into detail about this in my talk, although I will touch at a high level at the end about the challenges of this ecosystem. But in our paper, we do initiate the study of how to correct for these errors at the source embedding, and I encourage you to take a look. So now I'm going to talk about our system, Bootleg. And first, I'm going to address the fundamental question of how do you actually disambiguate over the tail? And the answer, as I hinted at earlier, is to actually use structural information over types and relations. So before going into the details, I'm going to give a high-level overview of how NED systems work. So the input is a sentence, and the output is the entities that participate in the sentence. So the first step is what we call candidate generation. And this is where we generate possible candidates for the mentions. So in this case, the mention Lincoln could have candidates of Lincoln, Illinois, Lincoln, Nebraska, or Abraham Lincoln. For each candidate, we generate an entity profile, which has metadata associated with each entity. And we use this to generate an embedding, an entity payload, which gets fed to our neural model, which then outputs the most likely candidate. So now we're ready to dive into these structural resources that I hinted at earlier. So disambiguation, as I'm going to show, actually requires learning information over text as well as over relationships and types, and that these three different sources of information actually form a hierarchy. So to motivate and understand this, I'm actually going to go through some examples. So if I asked you, where is Lincoln in Nebraska? Or what year did Steven Spielberg make Lincoln? You'd be able to know that the first refers to Lincoln, Nebraska, the city, and the latter to Lincoln, the movie, as the words Nebraska and Steven Spielberg commonly co-occur with each entity. So this is a pattern that you can learn on the entity level, which is an association of textual keywords. However, because these patterns are associated per entity, they are not going to generalize to other entities. Just because I learned something about Nebraska, Lincoln, Nebraska, does not mean I know anything about other cities in Nebraska, for example. Now, alternatively, you can also disambiguate with knowledge graph relationships. So take the sentence, David and Victoria Mitchell added spice to their marriage. The only way you're going to know that the answer is Victoria Mitchell, the poker player, not the runner of the same name, is that only the poker player is married to a David. So NED needs relationships in order to disambiguate, and relationships that are associated with keywords, for example, about what it means to be married. Now, critically, knowing something about what it means to be in a relationship does generalize to other entities. If I know about what it means for two entities to be married, I can transfer that knowledge to rare married entities and know what the right answer is for disambiguation. Now, types also have patterns where you can associate keywords with different types. For example, in the question, how tall is Lincoln, you know that it's referring to the person because people have heights, not places or brands. Similarly, what is the cheapest Lincoln has to refer to the car company because car companies have prices, or cars have prices. And if you have how many people are in Lincoln, that has to refer to the city, not the person or the brand. Now, these patterns are over types, and their phrases associated with each type. And again, this is another pattern that does generalize to other entities. Knowing something about what it means to be a person, the type person, can transfer to rare people. So as we just saw, there are these three different patterns that have different generalization abilities, specifically with the text memorization pattern having the lowest generality, meaning it's at the bottom of our pyramid. To motivate the rest of the hierarchy, a simple analysis of Wikipedia reveals that 22% of entities have a relationship, and 126 of them occur more than 100 times. And this means that we can actually learn patterns over these relationships that can then again transfer to these other entities. Now, as types occur even more frequently than relationships, we're going to put those at the top of our hierarchy. So the key takeaway here is that learning disambiguation patterns over types and relationships will help generalize to the tail, while pure textual memorization will not. So now I'm going to answer the next question, which is how do you actually train a model to learn patterns over entities, types, and relationships? And the solution that we use in Bootleg is to actually use embeddings. So if you recall our high-level NED overview slide here, I'm now just going to focus on these two components, which is the entity payload and the model itself, but I encourage you to look at the paper for the details of the rest. So to understand how the payload is generated, let's break down what happens for a single candidate. So take the Logan County, Illinois candidate and its associated profile. We first go ahead and actually query, again, we're using entity embedding, so we go ahead and query for the embedding for the exact entity of Logan County, Illinois, and add that to the payload. We repeat the process for KG relationships, where we get its relationship embeddings, and for its types. Now, fundamentally, what this means is that every single county type is going to get the same embedding. So patterns learned over popular counties are going to transfer to rare counties through this embedding. So these embeddings get projected down and turned into our entity representation. And critically, again, we have a component of this entity payload that is mapped to each layer of the hierarchy. So this payload information, as well as the sentence information, is used into our neural model. Now, this model is as simple as we can make it. It uses the now standard transformer module to learn patterns between text and the entity payloads that contain our entity, type, and relation embeddings. More details about the architecture are going to appear in an upcoming machine learning paper, but the high-level takeaway is that it's the simple model that supports reasoning over types, relationships, and entities. So I just went over how we generate our payload to disambiguate entities, and I'm now going to show some high-level experimental results showing that Bootleg not only achieves state-of-the-art on NED benchmarks, but also provides significant lift over the tail compared to a text-based baseline and helps on downstream production tasks. Overall, we see that Bootleg matches or exceeds state-of-the-art on 3 NED benchmarks. However, this really isn't where it's interesting. As I said earlier, the tail is where it matters. And this is where we see a dramatic improvement of baseline compared to a BERT NED baseline, which again just memorizes text. You can see that the Bootleg is within about 5 points of this BERT baseline model, and again, we didn't tune either of these models that much, and so this could potentially be closed just with better tuning. However, it's over the tail where you see over 40 F1 point lift between Bootleg and this text-based baseline model. Another subtle point here is that overall metrics can be very misleading when it comes to model performance. Lastly, we included the Bootleg embeddings into an overtime production task answering factoid queries at Apple. And here we see that there's an 8 to 17% lift in the production task, even over multiple languages, showing again that the real benefit of NED systems is in using these embeddings into downstream tasks. So lastly, I'm going to quickly highlight what I hinted at earlier, which is how do you actually manage and maintain these embeddings when you think about them with respect to these downstream systems? And I'm calling this a sort of embedding ecosystem. And the answer is actually going to be data engineering. So the life cycle of entity embeddings starts with training the embeddings with structured and unstructured data from Wikipedia, Wikidata, or other knowledge bases. As I mentioned earlier, these are then integrated into downstream products. Now, there are challenges associated with each step of this pipeline, from managing and versioning the data and embeddings to discovering errors and monitoring quality. In our paper, we focus on the problem of actually managing data and discuss how you can actually fix errors that arise in downstream systems at the source embedding. Some preliminary proof of concept experiments show that we can realize a 2 to 12 F1 point improvement in fixing targeted errors through data management techniques of augmentation and weak labeling. So please check out our paper for more details, but the high-level takeaway is that actually maintaining an embedding ecosystem where embeddings are used in these downstream systems is not a machine learning problem, but it's actually a data management one. So this is our system Bootleg, a clean, simple, open source NED system designed to tackle the tale of industrial NED. I encourage you to take a look at the link below for our code and tutorials, and please email me with any questions. Thank you.